Yes, very good morning. Uh, so, the last lecture we have done a very quick review. We have not gone through much detail about that. What was the necessary? I have tried to recall. And if somewhere else is also necessary, I will try to make it possible during the lecture as well. Okay. Or it is the best that you will yourself do this revision of your previous course. Okay, at least you should get an take an overview of the lectures, analysis of functions of single variable and ODEs. Okay, or lecture slides, whatever you have, lecture notes. Some of you have might have prepared. Okay, so you may circulate each other and all. That. Fine. And uh, I I was looking at some of the application point of view to start with. Unfortunately, my laptop was not working yesterday, and still it has some issues right now. Okay. So I may not be able to uh, give you the application today's lecture. Maybe we will have one application in next tutorial. Okay? Till that time, the problem of this laptop will be resolved. So, okay, and till that time, you have to clear with some of the very rigorous theory as well. Okay, and like some of you also have asked during the meeting that what are the uses and what are the applications and how to use them in real life and so on. So many questions. Okay, and those were even interesting. And you will, as already I have shared you the evaluation policy and the course contents with you. And also in the first lecture, I have told you that we are going with the uh, defining some of the problems in terms of some real life applications where we will look at the uh, use of these theoretical things. Okay, and you will try to get a flavor. However, still some of the concepts need to be introduced before solving real life applications like linear algebra. You should know how to solve system of linear equations numerically and so on. So it's not that it's like real life applications are only using this only. With this, what are the applications? There are some limited things. So you have to also understand that. Okay. It's not like why I have this learned the function of single variable, why I have learned function of two variables, three variables, OD, PD, and so on. So they all will combine together will be applicable in a real life purpose. Okay, for example, right away I may give you that what currently we are doing is we are solving some image demerging problem where we are suffering with the fourth order partial differential equation, and it is a very challenging issue to define the well posedness of the problem. And like in the analysis of single variable, you have seen the Picard's theorem. Okay, and I don't know how many of you are able to recall and how many of you have taken interest in looking at the well posedness of initial value problem like first order differential equation along with the initial condition. Okay, so that was even too challenging, and we have also looked at the existence uniqueness of ordinary differential equation of second order. And if you talk about nth order linear ODEs, then we can certainly devise them into system of first order differential equation and so on, and we can still talk about the existence and aliens. But when a question comes about partial differential equations, okay, it's really highly challenging, even for the existence of the solution, uniqueness of the solutions, and doing all the stuff. It's like very very well known partial differential equation. If you maybe come up with that in somewhere post, if you have its computational fluid dynamics or thermodynamics, somewhere you will see Navier-Stokes equation, and which is very much useful in modeling two-phase flows, bubbles, droplets, and particles, and so on. Okay, so reach and these days now, reach mathematics is required to get a good results, good papers, as long as when also to relate with the real life problems. Okay, so mathematics and computing this plant is you are getting a chance to learn the concepts in depth. Okay, and try to learn that because it will be definitely help you in doing interdisciplinary research and or whatever means like one of my friend is using artificial intelligence and this data science, okay, with along with mathematics in some companies. So industries are also looking for that. So you should not demotivate yourself that I am learning only the theoretical things and it is not useful. Okay, right. So as soon as means like we will introduce some more concepts, and then we will try to deliver applications which will be limited as far as means we are aware about the concepts so far. Okay, right. I think we can start now the lecture. So as previously told that name it a function of single variable, two variables, three variables, and so on. So these several in particular, instead of two variables, we will say that several variables. So they should be generalization of the first one variable, single variable. Right? Okay. Why? Because when you line down, or you can say you are projecting your problem onto the one-dimensional case. So this two variable means two dimensional, three variables means three dimensional. If you include more and more variables, that many dimension you will have. Okay, right. So some people also will try to understand, okay, up to three-dimensional space, we can understand, like people walking on a room or on a road. So you have all three dimensions. What is four dimension? Can anyone tell? How do you define the fourth dimension there? Ever you have thought about it? It's like somewhere if you have learned like dimensions like one dimension, two dimensions. So 2D plane, XY plane you have seen. XYZ space you have seen. What about like say XYZW? Some of you might have visited some of the museum or somewhere where they say you have enjoyed seven-dimensional seven-dimensional scenario, five-dimensional rules and so on. Yeah, it's like I would not recall your name, but yeah, you are right. So if you add one more dimension like time, yes, fourth dimension, yeah, and sensing. If you sense something like sometime when you riding like in a four dimension, if you put one more dimension, then there will be some sparkling. Okay, so you will sense also, sense will also introduce one more dimension and so on. Okay, so they are very beautiful if you like try to get examples from your real things. Okay, right. To know that, you find hard to okay, listen me in theoretical cases. That's fine. Yes. Okay. Right. So let's come to this two variable case. So once I define for two variable case, okay, that can be straightforward generalized for the three variable and four variable. So in a single variable case, when you talk about the limit, so function of two variable is function of x comma y. And what means what we are taking is like, and that is a real one. That's the very first thing we should understand, that what we are talking about limit of functions of two variables or one variable or three variables, and so all are real values. Okay, so means like your domain is, if I define this domain is a subset of, you can say, R cross R. Okay, so R cross R is a Cartesian product. Sometimes it is also known as R square. And how this is defined as this the pair of points A comma B such that A belongs to R and B belongs to R. This is how the set of all points. Okay, so whose domain is a subset of R cross R and whose values are lies in the regular. So similarly, you can extend one more dimension now, A comma B comma C, R plus R of Q. That's the space. Okay, and this is generalization. That one first step. Now, you have looked at when you talk about the limit of function of single variable. Okay, so like on the real line, you right. Now you are looking at the limit at a point, let's say C. Okay, limit at the point C. Okay, just a second. Yes. So when we are talking about the limit of function of single variable at a point C, or let's talk about A, okay, which we are generally aware about. Okay, and we are saying limit x tends to A, f of x. Okay, so what are the possible directions we can move towards A? So there are two directions on the real lines. One is this side and from this side. So that's why you have to talk about the concepts of left hand limit and right hand. X tends to A plus f of x. And what we have seen is whenever these both will exist and they are equal, okay, then we denote this is equals to limit of x tends to A f of x. Right? If we are able to recall. Now, on the other hand, if you're looking into the two-dimensional case like xy variable, okay, or xy plane, okay, just xy. Okay. So when you look at this xy and you have this, let's take x naught comma y naught is any point. X naught comma y naught. Okay, so I want to reach this point. How? What is the direction? Or what is the path you can choose? So x naught is you have this is right. This is your x naught, and this is your y. Okay, this is your x naught, and this is your y. Okay, so when y naught is fixed, you can reach out from this to this. Like suppose you want to reach from this point. Let's say decide 0, 0. Okay, I want to reach out x naught y naught from this origin. How many ways I can reach? There are infinitely many ways actually. So one way is 0, 0 to x naught and then x naught to x naught. Another path is this to y naught and then here. Okay, what is another path? Is a straight line passing through x naught y naught. Or there is a parabolic path. Okay, there is a cubic path, and so on. There are infinitely many ways to reach. So there is no concept of left hand limit or right hand limit or so on. So this x naught y naught can be reached by multiple paths, infinitely many paths. So now, if I come for the epsilon delta definition here, what was that? Is for every epsilon greater than 0, there exists a delta such that mod of f of x minus L is less than epsilon whenever 0 less than limit concept, right? 0 less than mod x minus a less than that. So whenever x is approaching towards a, if you take delta as small as possible, f of x is approaching to L. Okay, means whether from the left or right. So this was the concept for epsilon delta definition. Now, if you look at the closely for this this definition, mod of x minus a, what it defines or what it signifies on the real line is a distance, right? From the point a, x and a distance, modulus function will define the distance between these two, right? So in the two-dimensional case, we have that also flavor, right? Distance one. So that's one that is going to be generalized. So instead of mod, which means like later on when you when you will be introduced with the concept like norm, so it will be replaced by norm. So I am not going into that, but what I can do is for a given epsilon bigger than 0, there exists a delta bigger than 0, such that mod of f of x comma y minus L, L is the limit, less than epsilon. So for every epsilon, and whenever 0 less than that. So what is the distance? So I have only decided 0, 0 to x naught y naught, right? But this 0, 0 is not, you can reach from x comma y, and point can be lying in anywhere in domain. Okay, so this is the domain of, you can say this is domain of R. Domain of F. Okay, so this x of y will reach to x naught y naught along to any path. So what is the way of decide the distance between this is, right? You know, the square root of x minus x naught whole square plus y minus y naught whole square. Okay, the sorted distance formula, you know, right? Square root of this. Okay, that has been generalized. And so what it says as x and y approaches to x naught y naught, then f of x y approaches to L. So is roughly what you can say this f of x comma y as approaches to L whenever x comma y approaches to x naught comma y. Now in this fashion, I think now you can generalize it to three variable as well. So if I want to write in three variable case, so three variable case is for every epsilon bigger than 0, there exists a delta greater than 0 such that mod of f of x comma y comma z minus L is less than epsilon whenever 0 less than, still the distance concept will be the same. One more direction is included, x minus x naught square plus y minus y naught square plus z minus z naught square less than 10. And so on. Now you can include as many direction as you wish. And then you will add one more sum here and so for further bits. Okay, and in that case, whenever this happens, you can write that limit x comma y comma z in this case approaches to x naught y naught z naught. F of x comma y comma z is equals to L. Similarly, for the two variable case, you will write that limit x comma y tends to x naught comma y naught f of x comma y is equals to L. Symbolically, you can say, okay, symbolically. Okay, or you can say mathematically or symbolically. Okay, right. So let's have to find the concept. So this is here. So I have to just read out it. Okay. So we say that the function f of x comma y approaches the limit L as xy approaches x naught y naught. And we write this is as symbolically or denote, you can say, if for given epsilon there exists a delta such that for all xy in the domain of f is equals. And this is really challenging, okay, to establish the existence of the limit, because you don't have a single path, you have or two paths only, you have infinitely many numbers. Okay, right. Now suppose these things are valid, okay, and means like, so it's how the algebra of the limits will work here. So like a single variable case, you will also have the same flavor here. Okay, means what do I mean is, suppose you have two functions f and g, okay, and suppose you have established or it is given to you, or somehow you can find out the following. Okay, that limit xy tends to x naught y naught f of xy exists and equals to L. Limit xy tends to x naught y naught g exists and equals to M. Then what about the sum? What about the difference? What about the product? Similar as single variable. Okay, so some rule says it's a sum rule. So when you perform the sum of these two functions and then apply the limit, that will give the sum of the limits. Means by so this is a linear, you can say. Okay, this is the definition of a linearity with respect to sum. Okay, difference. So difference you should have the order. So if you have taken f first and then g second, so first is the L limit of f, then limit of g. Here doesn't matter, first you take g or first you take f in addition, but here it does matter. Similarly, in the product rule, so if f and g both are in the product, and suppose you know the limit of xy tends to x naught y naught both exist, so the limit is nothing but the product of the limits. Okay, and now similarly you can identify the quotient rule. Quotient rule means you have this g, suppose you have f by g, rational type of function. Okay, rational functions. So suppose you know limit of xy tends to x naught y naught f exists and equals to L. Limit xy tends to x naught y naught g exists and equals to M. And I can't straightforward say that limit xy tends to x naught y naught, this rational function is going to be L by N. I can't say always. What I need to be make sure that g should not be 0. Okay, g should not vanish. Okay, so that this rational function is well defined. That's a very first thing. Okay, and another thing is the limit of g is also should not be 0. Okay, so there are two things: g should not vanish and the limits value also should not vanish. Then everything is fine. Okay, so you have to take care of the points where the denominator gets vanishes. That's what in the you can say in a more appropriate way. Okay, what I can mention. Okay, right. Okay, so this is how the question rules here. M is non-zero and g also should not vanish. So constant product rule, this is simple. G if you take k, so it's a constant, limit is constant. Okay. Now this is a very important message. So sometime you have suppose you know cos of x into y, suppose you can find easily, but suppose you have been given with like 2 to the power 2 by 3, what to do? Okay, so it is not that easy to handle epsilon delta definition in this case. Okay, even two variable case. Okay, you can't talk about three variable and fourth variable if you go with the very rigorous mathematics. It is not possible always. So you can certainly refer some of the rule, provided some of the things should be verified. Okay, so what need to be verified? If R and S are integers with no common factors, means their GCD is 1. Okay, greatest common divisor. Okay, and S is non-zero because it is in the denominator. That can be easily verified. Now, if the limit of xy tends to x naught, y naught, f of xy exists and equals to L, then this limit of this power function, this you can say power rule, will give you the limit of f of xy to the power r by s, that is L to the power r. Okay, right. So I have one, I think, problem now. Let's look at it. Okay, and I have taken a very simple problem. I'm telling you. Okay, it's not that much tough, so that we can apply epsilon delta definition easy. Okay, so apply the limit definition and find the value of this. Okay, so I have this. I want to see limit x comma y tends to 0 comma 0. 4xy square divided by x square plus y square. Now look at this. This is a rational function. Okay, numerator is 4 times x times y square. Okay, positive powers, and denominator is x square plus y square, kind of polynomial in x and y. Okay, they are looking nice functions. Okay, maybe later on what we mention is continuity, differentiability, and so on. Then you will slowly understand what do you mean by nice functions. Okay, means which are smooth. Okay, and so on. Now we want to understand the limit of this. Okay, so near the 0 0, so tends to 0 0. And now if you look at, if you straightforward substituting x equal to 0 and y equals to 0, it is 0 by 0 indeterminate form. So you can't do that. Moreover, you can't simplify it. Okay, now before applying epsilon definition, epsilon delta definition, what is the suggestion here is that you look at the a function closely. F of x comma y is equals to 4xy square divided by x square plus y square. Now what you need, so you need to first guess what should be the L. So you need to identify L value. Okay, so then only you can start with. Okay, so how to identify this L value here? Okay, so for that purpose, so you have here in 2 dimension xy, and you want to reach this 0 comma 0. So there are various ways to look at it. Okay, so you can have this x comma 0 to this point, and you have this is y comma 0 to this, oh sorry, 0 comma y to, or you have this the line y equals to x. They are very simple paths. Okay, y equals to x, or you can, if you are not satisfied, you can look at y equals to x square. Okay, so to reach out this point 0 0, so along, so let's see, along x-axis, what is the value of f? Along x-axis, what is f? F of x comma y means along x-axis means y is 0, but once y is 0, it is 0. So along x-axis, I'm not means like xy is, I'm saying non-zero. Okay, that's what I'm mentioning here. First of the first thing is xy not 0 along x-axis. Similarly, along let's say y-axis. Okay, so f of x comma y is again 0. Because denominator, see, you can look at the denominator. Whenever xy is non-zero and along x-axis y is only 0, so x cannot be 0. So the denominator will never vanish. So all but the numerator will get vanished because of the presence of y is equal to 0 or presence of the x equals to 0. So along y-axis f of xy is 0, along x-axis also f of xy is 0. Okay, let's look at the line y equals to m of mx. Okay, along y equals to mx. So what is f of x comma mx, y equals to mx, right? 4 times x, y is what? Y square, so mx whole square divided by x square plus y square, so that is mx whole square. So now this is equals to 4x cube m square divided by x square times 1 plus m square. If you simplify it, so what you replace, for what you get is 4m square by 1 plus m square times x. And now, you know, if x is tending to 0, this is also tending to 0. Right? So if means allow y equals to y equal to mx, okay, so limit. So what you have is just limit x comma mx tends to 0 comma 0, f of x comma y is 0. So this path tells you the initial guess that, see, everywhere the final value is 0. If they are different, you can straightforward say that the limit does not exist if you are getting different values. But if you are getting all the values, you can't say that limit does not exist or limit exists. Okay? So now, so you can also check another path like y equals to x square or mx square. Still you will get the value 0. So that I left it out to you to check the path. Okay. So I just verify. I will just verify that along that f of x comma, you have, this is, let's say, mx square will tend to 0 as x tends to 0. Okay, that you verify. It's very easy, substitution and then finally single variable case. Okay, now, so what is the initial guess? If limit xy tends to 0, 0, f of xy exists, then L must be 0. Okay, if this happens. Okay, so L equals to 0, you can start working. Now, let's say let epsilon greater than 0 be given. Now, mod of f of x comma y minus L is equals to mod of 4xy square divided by x square plus y square minus L. L is 0. So that is equals to mod of 4xy square by x square plus y square. So that is equals to 4 times mod x times y square by x square plus y square. I don't need to put mod here because this is already non-negative. Now, if I use some mathematics here, so I'm saying that this is going to be less than equals to 4 times mod x. Why? Because it is very simple to see that y square by x square plus y square is less than equals to 1. Okay? Right? So if so this is there, so this implies this less than equals to 4 mod x, epsilon greater than 0 be given. Now what you need to do is, now you have to say, you have to find out, identify delta which satisfies so and so. Now, not that mod x is less than square root of x square. Right? So this is going to be less than square root of x square plus y square. Right? Less than somewhere, so you have, this is 4 times mod x, 4 times this, 4 times. And what I wish now to identify a delta greater than 0 such that 0 less than square root of x square plus y square less than delta. So suppose I take this square root of x square plus y square is less than delta. Okay, because I want this. There exists delta such that this happens. So you have, again, we have to create an artificial, either epsilon or delta. So this is going to, so now not that for mod x is less than this, or you can say less than equals to, you can use, okay, which is less than 4 times delta. Now, which is going to be less than epsilon whenever delta is less than epsilon by 4. Okay, yes, right? So you can choose delta equals to epsilon by 4. You can choose delta equals to epsilon by 4. I can say this is equals. So this establishes the definition. Okay, either you choose any less than epsilon by 4 number, or you can choose equals to epsilon by 4. Both will be okay. So you got, so not that this happens. So this together, what will imply? So this together implies for epsilon bigger than 0, there exists a delta. So what is delta is less than epsilon by 4. Okay, and in fact, what we can do is I can say delta is belonging to, you can say 0 to epsilon by 4 open interval, or you can say it's close here to the side. Okay, there are infinitely many numbers we have encountered actually, such that mod of f of x comma y minus L is less than epsilon whenever 0 less than scale root of x square plus y square plus. So this tells you that the limit of x comma y tends to 0, 0, 4xy square divided by x square plus y square equals to 0. Okay, right. Now, so I have given one example. Let's see when we'll handle the other concept as well. So there will be mixed examples. Okay, okay. Now, the limit to the next is, now we can look at the function, look at the another concept like continuity of the function of two variables. Okay, not that means like it is again will be the similar case, or you can say it will be looks like as a simple generalization of a single variable. Okay, again, so here it is 0 is not included within, right? There your 0 will be included. Okay, this you can, another way is, this is a deleted neighborhood. If you recall the word from the analysis of function single variable, this is a deleted neighborhood because you have punctured the point 0, 0 from the neighborhood. Okay, but in the continuity case, you are including that point, means you are taking complete neighborhood. What is the difference there is, in the limit case, function may or may not be defined at the point. Okay, but in the continuity case, function has to be defined and has some values. Okay, so if you recall from the single variable case, that is the major difference between the limit and continuity. Okay, right. And then limit value should be equals to the function value at that point. Okay, right. Okay. So here is the definition. A function f is continuous at the point x naught y naught. So I'm just giving you simple. If f is defined at that point, second, the limit exists at that point, and then the limit value should be equal to the function value. Note that again, algebraic combinations of continuous functions are continuous. What does that mean? Again, you have the same freedom what you have enjoyed in the function of single variable. Means if you take two functions which are continuous at a point x naught y naught, then their sum, their difference, their product will also be continuous. On the other hand, when you talk about the rational type of function, is like f of xy divided by g of x comma. So you should verify where the function is get vanishing. Those points should not be the part of the variable. And if f and g both are continuous, okay, and g value at that point x naught y naught is not 0, okay, then the function, the transfer function is also continuous. Now it will be easy to now for you the case for xy square divided by x square plus y square to look at, okay, to decide the continuity of the functions. So that we are going to discuss. Okay, right. So, okay, so we have the straightforward examples now. So discuss the continuity of the following. So let's try to discuss this. Yes, first we will discuss this, then second, first and third. Okay, now let's first, because just now we have seen the limit exists and equals to n. So we have seen, so f of x comma y, I've just defined f of x comma y is equals to 4xy square divided by x square plus y square. So I'm defining this function, this as whenever xy is not 0 and 0 when xy equals to 0. I'm defining this function. Okay. Now, just now we have verified that, so this definition gives you f at 0, 0 is 0. If I define this function as this, okay, then this will give you f at 0, 0 is 0. I have defined. Forcefully I have defined. Okay, please understand it. I have forcefully defined that at 0, 0, the value of f is 0. I'm assigning this value. And for non-zero xy's, these are the values. 4xy square by x square plus y square. So what this definition gives you is f at the point value is 0. Now, what we have seen that limit of x comma y tends to 0, 0. That f of x comma y, just now we have shown that is equals to 0 and that is nothing but f at 0, 0. So this establishes the continuity of this at 0, 0 if you have the following definition. Okay. Now, suppose I rewrite this. So let's say I define G. I'm just giving you an example. Okay. Let G is defined as 4xy square divided by x square plus y square whenever xy is non-zero. And see, if I am free at here to define value at 0, so I am also free to define the value as any constant k, any constant I have to, xy equals to 0. Now, we have seen that limit. So now, okay, now I want to look at the continuity of this function. So please look at it carefully. Now, whenever xy is non-zero, so denominator and numerator, what are those type? So numerator, if you look at, let's say, G1, okay, G1 equals to 4xy square. This is G1 of x comma y. Let's say G2 of x comma y is x square plus y square. Okay. Now, it is easy to verify that this function is continuous. It's behave like a polynomial of degree 3. Okay. It is easy to verify that you can verify that G1 is continuous. Similarly, G2, this definition is again a polynomial of degree 2 almost. Okay. It behaves like that. I'm not saying it's a polynomial of degree 2, but it behaves like that. It's a nice function. Okay. So it's going to be a continuous function that is very, you can verify easily. Okay. For every x comma. For all x comma y belongs to R square and different. So G1 is continuous, G2 is continuous. So their division will also be continuous everywhere except at the point where the denominator vanishes. That's what we have just now learned. Right? So now the denominator vanishes at the point only 0, 0. No other point. Right? So we need to check only the continuity of the function at 0, 0. I hope you understood. Okay, so this is a rational function. where numerator is continuous, denominator is continuous. So this rational function will also be continuous, provided the denominator should not vanish. Okay, so denominator will vanish only at the point 0, 0. So there may, if there are multiple points, those points you have to check the continuity. Rest, the function is continuous by following the algebraic views of the continuity. Okay, so now you need to check only the point at 0. Now, also we have known that limit of this g as xy tends to 0, 0 is going to be 0. So limit value is 0. That also we have seen. Now, for continuity, that limit value should be equal to the function value at that point. But that only will be true when k is. So if k is different from 0, then the limit value is not equals to the function value at that point. So function is not continuous at 0, 0. Okay, so to make it continuous, we are forced to put this value as 0, b. So these type of questions are also the part of your GATE exams. Okay, they will ask you to identify this k so that the function becomes continuous. Okay, so I hope I have made it clear that how do you look at the rational. Okay, now this is the discussion about the second one. Okay, now let's look at the first part. So I given with f of x comma y is equals to 2xy divided by x square plus y square. I divided by x square plus y square. Now I want to look at the continuity of this function. Now, very first thing, this function is not defined at 0. Because when you take x equals to 0, y equals to 0, then this is 0 by 0 indeterminate form. So at 0, 0, you don't know what will be the value. Okay, let's try it. If suppose the limit exists, we will define the limit value at that point. Okay, and that then we make it, we may say that along with that, it is going to be continuous. Now, this look at this. So if you look at the carefully, the numerator is continuous, denominator is continuous, so rational function is continuous everywhere except at 0, 0. That there is no doubt about it. So you need to check the continuity at 0, 0. Rest points in the R2, this is straightforward continuous function. There is no point to talk about. Okay, it's very sure. Now, only need to check at 0. Okay. Now, look at the numerator and denominator carefully. You should understand that x and y. This is x into y. So, I am going to focus on the variables, not on the constant. That's very first thing. Wherever they are. So, why it is so? Because see x into y, when you have the product. So, variable also has some powers, one here and one here. So total power of this term is 2. One from coming from here, one is coming from here. So 1 plus 1 is 2. When they are sitting in the product. When they are sitting in the division, x by y, suppose the power of this is means when you have division, you have subtraction. When you have product, you have addition. I hope that can be understood very well. Okay, so the numerator can be understood as of degree 2. Similarly, suppose you do take careful look over x square plus 1. Each term, so when you have addition or minus, so you have to look individual term and see what is the highest power. Okay, so then you can recognize that as a degree term. So now if you look at the both term that has the degree 2, so it's commonly it's going to be power. Now, both degree matches. The numerator degree is also 2, denominator also degree. I have already told you that I will not bother about the constants. So wherever they are sitting here or there, it doesn't matter. Okay, I'm only focusing on this. Right? Now, so both has the same degree. Looks like, okay? Now, what happens is when you have the same degree, most of the time the limit does not exist at 0. Okay, you will lose. Now, along x-axis, similarly, so along x-axis, okay, when you have x comma 0 is not equals to 0, 0. Okay, I'm mentioning here. So f of x comma 0 is 0. Along y-axis, if I'm looking at the behavior of this function, f of 0 comma y is again 0. Again, here 0 comma y is, I'm identifying that as non-zero. Now, again, along y equals to mx, the line, straight line, passing through 0, 0 point. Okay, so these are infinitely many lines, right, passing through origin. So then f of x comma mx, replace y equals to mx. So what you will receive is 2 times mx square divided by x square plus y square is m times x whole square, so m square x square. So now this x square will come out, and what is remaining is 2m by 1 plus m square. So for different values of m, it will be different, right? So what we observe is, so this implies f of x comma mx is equals to what we have got is 2m by 1 plus m square. So whenever m equals to 0, that is 0. M equals to 1, the value is 2 by 1 plus 1 is 2, that is 1. When you have m equals to 2, that is 4 by 5. Okay, and so on, infinitely many different values. So from here, this observation, what we can say, the limit does not exist. Because when you take the line, this is the line y equals to x. This is along the line y equals to 2x. So another line is y equals to 3x. So along every path, it should take value, unique value. Then only you can talk about the existence of the limit. But along, this is the difference. So once you get along one path with a different value than previous one, you can still over there say that the limit does not exist. Okay, so therefore now this implies limit x comma y tends to 0, 0, f of x comma y does not exist. So if the limit does not exist at a point x naught, y naught, then it is not continuous. Straightforward. Okay? Right. Now, let's talk about the third part now. Now, third part is, now for third part, I will give you the idea. So we are going to look at now third, 2x square y divided by x4 plus y square. So you have, this is f of x comma y is equals to 2x square y divided by x to the power 4 plus y square. Okay. So now I can comment here straightforward that numerator is continuous, denominator is continuous. So this rational function is continuous everywhere except at the point where denominator vanishes. Okay, so denominator will vanish only at the point 0, 0. You can look at the power x power 4 plus y square, 4 power of even power. So there is no point of negative. So this is only possible 0, 0 at point 0, 0. Okay, so you need to only check at 0, 0. Okay, right. So now, so we can straightforward check the continuity at 0, 0. Okay, so along, so first we have to check whether this limit exists or not. So along, let's say x-axis. So these are very elementary things. Okay, along x-axis means x comma 0. That is it. So whenever x comma 0 is non-zero. Okay, along now y-axis. f of 0 comma y equals to 0. 0 comma y is non-zero points. Okay, now again let's check the along y equals to mx. So what is f of x comma mx? That is going to be 2 times x square times y. So y is mx. So y is equals to mx. So 2x square times, so 2mx cube divided by x power 4 plus x square. So y square. So y square is m square times x square. So that is going to be, you have, this is going to be 2mx divided by x square is common, x square plus m square. Okay, so again we are not taking 0 point. Okay, so m is non-zero. Okay, I'm talking about m is not 0. Okay, so this again tends to 0 as x tends to 0. It's very simple. So all of them are suggesting you to say that this is going to be the limit is exists and equals to 0. Now, but look at the path now. Now, let's take along, let's say y equals to this parabolic path, mx. Okay, along y equals to mx square. So that is going to be x comma m times x square. So that is 2x square times y, that is mx square, divided by x to the power 4 plus y square is m square times x to the power 4. So that is equals to, now 2x to the power 4, x power 4, x power 4 will get cancelled. You will have 2m divided by m. Now for different m, you have different values. So this is equals to, you have 0 if m equals to 0, but we are not taking m is we are taking non-zero, so there is no matter to talk about. If m is equals to 1, you have this is 1. If m equals to 2, then you have 4 divided by 5 and so different values. So this says that limit x comma y tends to 0 comma 0 f of x comma y does not exist. Means this is not continuous. Now the question comes now that it's like how to how to get that intuition. Okay, that y equals to mx square will have a will be showing you that limit does not exist. Okay, now this the very first thing is this will come through the practice. Okay, the second thing is what we can do is little we can take care of the rational this function terms. Okay, now you can look at this x square x power 4. Now, when how this highest power is x power 4, how the numerator will have x to the power 4, that we have to try it out. So when you have x to the power 4, then only it will be get dominated. Okay, so I have that idea that if you take y equals to mx square or x square even, okay, then you have certainly x power 4 and there is somewhere that now after that you can look at carefully the next term. Okay, when you take y equals to x square or mx square, so y square will give you x power 4 constant multiple. So x power 4 will straightforward come out and get cancelled. Okay, so this is how this can be taken care. Okay, so you have to analyze numerator, denominator, powers, term wise, and so on, so that you get an equation. And again, you have to do lot of practice. Okay, right. Okay, so now we can talk about the continuity of composite functions. So now when you talk about the composite here, so you know, note that f is from D to R. What is D? D is a subset of R cross R square. Okay, and I want to make G compose with F. But F is a real value because F will give you a real value. So G can be acting on the single variable. G could be only single variable function. That should be very clear. G compose F D to R. So G of F of X comma Y belongs to R. Okay. So F of X, so what is the domain of G is the subset of real number. Okay, right. Now, so here you can understand now. So when you talk about the composition function continuity, so first that argument function. So this is the argument. So G of F of X. So this will treat as argument. This argument function should be continuous. So continuous where? At X naught Y naught. I'm talking about at X naught Y naught. So F function should be continuous at X naught Y naught. Then G function should be continuous at F of X naught Y naught. Then composition together will function continuous at X naught. Okay, right. So if F is continuous at X naught Y naught and G is a single variable function continuous at F of X naught Y naught, then the composite function defined by this is continuous at X naught. And how this help you is like we are having example. So if you take G is equals to, let's take G of X is equals to e to the power X. And I'm taking F of X comma Y as X minus 1. So I'm taking this F of X comma Y as X minus Y, and it's easy to see or verify that function is continuous. And now you can look at G also, E exponential function that you can verify that this is continuous. So what is G compose F? Is going to be identically e to the power X minus 1. So now X minus this function is continuous. You take any point, function is continuous at any point, and with this E also function is continuous at any point, which will never get done. So this is going to be continuous. Now, if you want to apply on the second part, so you have G compose F of X comma Y is equals to cos of X into Y divided by X square plus 1. So it is easy to extract now what is F of X comma Y is X into Y divided by X square plus 1, and G of X is equals to cos X. You know, cos function is nice function, continuous, even differentiable and so on. And now look at this F is a rational function. So numerator is continuous, denominator is continuous. This rational function is continuous everywhere except at the point where denominator vanishes. So denominator vanishes at the point where X squared is equals to minus 1, but it is not possible at the real life. So this will never get vanished. So F is continuous everywhere on the R2. Okay, so you take any point X naught Y naught, so F of X naught comma Y naught is continuous. F is continuous at X naught Y. And G is continuous everywhere. So at every point on the real line, so it also continuous. It's also real point. It's also continuous at that point. So composition theorem will tell you that G composed with F will continuous at X naught. Right? Okay. Okay. So now we can, so we are not directly defining the differentiability. We are going to first define the partial derivative of F with respect to X. So when you talk about F of X comma Y, and when you draw this on XYZ space, it's going to be a surface defined on some reason. Okay, when you look at this, Z equals to F of X comma Y along X, along Y, if you do everything along the Z line, it is going to be a type of surface that is going to be. Okay, that I will show you. Okay. Now, the partial derivative of f of x with respect to x, how will you define? Means, see, partial derivative. So, means you are differentiating partially. What do it mean? That with respect to suppose x, you want to differentiate. Means partially, means you don't bother about. Okay, means don't bother means like constant. Okay, y is constant. Means you are treating y as a constant. When you're differentiating partially with respect to x, you are treating y as constant or y as fixed. Okay, when you're dealing with the partial derivative with respect to y, then you are treating that that x is constant. Okay, fixed. Okay, and then you are moving along the line. That is how we can see. And then you are differentiating in that direction. That's okay. This is one the simple, roughly meaning of partial derivative. We will see the geometrically as well now. Okay. So it is very clear from the definition. If you recall from the single variable case, what was the definition? That you have the limit h tends to 0, f of x plus h minus f of x divided by h. Okay, now you can look at here. So function of two variable. So y naught is fixed. So there is no movement in y direction. Only movement in increment in x direction, and take the difference, divide by h, limit as then apply the limit. Okay, so if this limit exists, that will tell you that this is a dou f by dou x at x naught y. Okay, so this is a point at x naught y. Okay, now how will it be looks like geometrically? Let's look at it. Okay, now if you look at here, so this is a xy plane here. Okay, and this is a z. So z equals to f of xy. It's a level surface. When you deal with the vector calculus, that you will more understand what do you mean by level surface. So you have taken z equals to, let's say, 2, f of xy equals to 2, or f of xy equals to 3 fixed. Okay, so this is a equal surface z equals to f of x. Okay, and I'm dealing with the partial derivative with respect to x, and I want to understand the partial derivative at the point x naught y naught. Now, when I already I have mentioned, when you dealing with respect to x, you have to treat y as a constant. So now means y equals to y naught. So this is the x naught y naught point in the xy plane. You want to get the partial derivative method. So y is fixed means y equals to y naught. This is the line. Okay. Now when you stretch this line along the z-axis, when you stretch this line along the z-axis, then it will give you a plane parallel to z-axis, and it will intersect the surface. Okay, it will intersect the surface at some level, so that's going to be this. Right? You can understand that means like how this is going to be. So you have the xy. Okay. This is a right here. Let me draw x, and this is z. And when you have this is a x naught y naught point. And when you have this is y equals to y naught. And when you stretch it along the z-axis, it will be a plane, kind of window, okay? Two-dimensional window. Okay, you are stretching along the z-axis. Okay, and it will cut the surface along a line, or you can say curve. This is a curve which is obtained. So the curve z equals to, which is a curve, and along this curve, the y value is y naught, because it's a y equals to y naught is cutting this plane at this curve, and at this point y equals to y naught. So this is a curve z equals to f of x naught comma y naught. Okay, now finding this point, and so corresponding to this point, x naught, y naught, there is a point on this curve. So this is a point on the curve which is which is found by intersecting with the plane and to the surface. Okay, so this is a curve along this means this x naught y naught at this point, this f of x naught y naught is the value. Now I want to understand what is the partial derivative with respect to x naught. So we have already fixed everything. We have got the fixed curve now. Okay, now what you can do is at this point you have to do a tangent. Okay, I'm not good at drawing, but you can understand. Okay, so tangent at that point will give you the partial derivative with respect to x. Okay, so how to get that tangent here is that you take increment in the x direction, take the difference of x naught plus h comma y naught. That will be here somewhere here x, and this point is f of x naught plus h comma y naught, and this is the point where f of x naught comma y naught. Take the difference, divide by h, and they apply the limit. That is how this tangent is obtained. Okay, so this will identify the partial derivative with respect to x at the point x. So when you want to talk about the partial derivative with respect to y, what you will do? Rather going through the plane y equals to y naught, when I'm talking about the plane y equals to y naught means you draw the line y equals to y naught and stretch it along the z axis. That will give you a plane, okay, which is a parallel to z axis, y equals to y. So when you're dealing with the case partial derivative with respect to y at x naught y naught, instead of this we are going to draw the plane along the x equals to x naught, means parallel to z axis, and that will cut the surface on a curve, and that will give you, and along at that point that you will draw the tangent, and that will give you the partial derivative with respect to y. Okay, let's see. Okay, so I just have this here. Okay, yes, it's here. So you have this, so you have the curve, okay, and you have drawn the plane along the parallel to z axis along the line x equals to x naught. This is a plane x equals to x naught, and which will intersect the surface at some point. I mean, which will intersect along the curve. Okay, so this is the curve again. Z equals to, it's a curve z equals to f of x naught comma y. Okay, now you take the point here. This is the point f of x naught y naught. Okay, now you are talking about partial derivative with respect to y, and along this curve x is fixed now. Now you take the increment in the y direction. So so to differentiate between partial derivative with respect to y and with respect to x, instead of here h, we are taking k. So this is the only difference. So you take at x naught comma y naught plus k minus f of x naught comma y naught divided by k, and apply the limit as k tends to 0. And if this limit exists, that will give you the partial derivative with respect to y. Okay, right. So this is how the geometrically this partial derivative means. Okay, and so this is the fundamental difference. So, but when you deal with the problems, you are directly differentiating partially with respect to x or with respect to y, treating another variable as a constant. Okay, right. So let's okay. So let's leave these exercise for today. You can look at them. Okay, I will mail you this. Okay, this page. Okay, or you can say, or I can put it on Google Classroom. Okay, and try to solve these problems. Partial derivative with respect to x, with respect to y, and root over -5. These are very simple. Okay, try them. Okay, and we will do that the same in the next session. Maybe on that upcoming Wednesday, we can take these as tutorial. Okay, yes. So if you have any questions, you can ask. Yes, we are going to talk about the differentiability, total differentiability with respect to variables with at point x or y. What do we mean by that? That's our next goal.